Yeah, welcome to the next episode on using the ConceptBase system. My name is Manfred Joisfeld. Our topic today are numbers and functions. So on the right-hand side, you see two classes, integer and real. Well, they are called classes in ConceptBase because we don't have types in that sense in ConceptBase. Uh, Oddly enough, integer has only 6 instances, 0, 1, 2, 5, 7, and 10, and real has no instances. Oh, it does. It has 0 0.5, sorry. So just one instance, but certainly not the whole extension of real. We can also uh, show that in the Taylor's editor. So if you ask for the instances of integer, you get these here. Now, we can do some limited arithmetic in ConceptBase. They are mostly used in the rule and constraint language, but as a shortcut, you can also uh, evaluate arithmetic expressions in the Taylor's editor. So they are interpreted as a function call or functional expression, which themselves are special types of query calls that have at most one answer. So give me all integer numbers that are the sum of 1 and 2. There will be only one, and that is 3. So if we now check for the instances of integer, we suddenly have 3 as yet another instance. So let's see whether that also shows up here. Not yet, so we have to probably validate and show the instances. So now we have the number 3 here. So what does it tell us? The extension of the classes integer and real are built over time. These are not all integers or real numbers. These are the integers and real numbers currently used in the system. So either they are attributes of some other objects, or they have been evaluated as a result of some functional expression, and then they are stored as objects. So if we take the number 3, for example, then we have 3 as an instance of integer. It's an object. In principle, we could also add an attribute to this object, but we usually don't do that for values. So let's take another example, 1 divided by 3. That's up to this precision, this number, 1/3. And that should then also show up as the instances of real. So we have another instance of real. If we would want to have all the instances of these classes, then the extension would be infinite. We have infinitely many integer numbers, and the number of instances of real are even beyond countable. So we will not be able to enumerate all these instances if we would have arbitrary many digits after the comma. So that tells you that numbers are a bit a special thing in ConceptBase because they are created on the fly, and if we are not careful, we could end up with the creation of infinitely many objects. So let's take another example that is a function definition for Fibonacci numbers. So the Fibonacci is defined as a function the result is an integer number, so all the Fibonacci numbers are integer numbers. They are computed for a parameter n. If n equals 0, then the Fibonacci number is 0. If n equals 1, then Fibonacci number is 1. Otherwise, it is a sum of Fibonacci of n minus 1 plus Fibonacci of n minus 2. So let's tell that. And now the function definition is told, and we can call that. So Fibonacci of 1, for example, is 1. Fibonacci of 2, that's also 1. Fibonacci of 3, that is 2. Let's be a bit more brave. Fibonacci of 10 is 55, and so forth. So this recursive definition of Fibonacci will compute rather high numbers. We have now new instances of integer, so we have many more instances. Let's call Fibonacci of 30. That's this high number. Now we will have even more integers. All those integers that were needed to compute the results have been added. In this case, the recursive definition of Fibonacci numbers will terminate, so you will not create infinitely many integers. But I show you another example where this may come to a problem. So here you see the simplified representation of the Peano axioms defining natural numbers, starting from the number 1. So 1 is a natural number, and if you have a natural number n, then n plus 1 is also a natural number. If you would ask for all the instances of a natural number, then this would not terminate. It will generate more and more natural numbers, and the system would just loop forever and eventually run out of memory and crash. And that shows us that we have to be very careful with using numbers together with recursive rules in ConceptBase. That may remind some of you of the theorem by Gödel. So if you have a logic and add arithmetic to that, it becomes undecidable, roughly speaking. And so if you add numbers to deductive rules in ConceptBase, then you also end up with a system that may not terminate. So where the termination becomes undecidable. The next example is the famous Ackermann function, which is decidable. It will terminate, but it will become computationally intractable to compute values for parameters m and n that are greater than 3 or 4, roughly. So maybe I can tell that. And then if we call a of 2, 2, it will still compute the result. For a of 3, 3, it will also probably give you a result. But if you would call a of 4, 4, then Yeah, it will take longer than the time the whole universe has existed, and let alone if you would use higher numbers. Yeah, last example is integer logarithm to the basis of 2. So that can be recursively defined. Log2 is the function, and it is used in its body, in its definition. So if n equals 1, then the logarithm to the basis of 2 is 0. If it's 2, then it's 1, and if it's greater than 2, so remember we are in the integer domain here, then this is the recursive call logarithm of 2 of the integer division of n by 2 plus 1. So that's fairly straightforward. Let's tell that, and then we can call log2 of 8, for example. That's 3. Log2 of 10, 10. That is also 3. And log2 of, let's say, 100. That is 6. So that completes our discussion of numbers and functions in ConceptBase. So keep in mind that ConceptBase regards numbers like objects, but we only store the currently used numbers. That means if an expression would generate more and more numbers as intermediate results, then we would fill up the database. And if that does not terminate, then we will eventually run out of memory in the computation. So that's a very peculiar way of dealing with numbers in ConceptBase. We introduced that because we wanted to have a uniform representation, but we also have to pay in terms of creating new objects just for numbers. Note that if you compute results in a program, you also have to store intermediate results somewhere on a stack. For example, the case of ConceptBase, the stack is not just emptied. The definition of Fibonacci here is results in the naive evaluation of the Fibonacci number, but since intermediate results are stored, it will not recompute the Fibonacci numbers that have been computed already. So it will store the results, and then it will just use the stored results. So this, even though this is more or less the original definition of Fibonacci number, it results in the semi-naive algorithms for computing Fibonacci number. I think it's O of n, the complexity, rather than O of 2 to the power of n. Good, that completes it, and see you next time.